let's talk big business. Talking about the physics. We're talking about the things that happen when stuff hits other stuff, right? I mean, I hope so. I'd like to believe so. And this is just a very basic, shallow introduction to some ideas that I have no authority to talk about, but over time, I've done a few things that I think look okay, and I'm going to try and explain some of them. So, I finally finished the basics. They're all done, and it's a playlist, and if you know nothing about Flash, go and watch the basics, because you're going to need to know those for any of this next stuff. So, here we go. We're talking about the physics. We're talking about things falling that say big business on them, and then they hit the ground. So this thing, this item, it supposedly weighs something, and is heavy, and it's sort of big. Maybe it's like 1 foot by 1 foot by 1 foot back, as if it were a 3D cube, and it's gonna fall and then hit the ground, and I'm gonna talk about it. So when we can live under the belief that it is floating in space, or floating on Earth, or somewhere that has gravity, and then it starts to fall. So when it does, it doesn't start to fall immediately. Like, it starts slowly, because it has no motion downward right now. It's just at a dead stop, and then over time it'll start to fall more quickly, and quicker, and then quicker, and the distance between each of its frames, where it is in those frames, will increase as time goes on. This is called easing. It's the increase of speed or scale or any change over time. So the first gap is that big, and then on like a standard easing type model, it might double in size with every time, with every frame. Sometimes it might triple. Sometimes it might start by doubling and then go up to quadrupling. It all depends on your easing graph that might exist. So this one, the graph, in air quotes, for this might say this is time, and then this is distance traveled downward. It might look like this. It starts really slow, and then it speeds up right here. So it would like start slow as time goes on, and then it might jump. So like that. This is called an ease in, where the beginning not much happens, and then near the end it speeds up. And ease out would be the opposite, where it starts really fast and then slows down as time goes on. And you can see that happening on the rebound. So once it hits the ground, it comes back up. And at first, it comes back up in a big jump, and then the jumps get smaller and smaller, and it was a little ease out. And then as it heads back towards the ground again, it eases into falling, and over. It's just a bunch of different types of easing and differences in space over time. And you may be wondering, why did you choose to make it go off to the side there? Well, I could have not, and it probably would have looked fine just going straight up and down. But there's a lot of stuff in real life where when you drop it, it's not perfect. It's especially, like, not perfect when it falls, and not perfect when it's hitting the ground, and the ground is almost never, ever perfect. So most things tend to pick an imperfection and go with it and amplify it. And it kind of, I don't know, I'm trying to emulate real life to some extent. But I'm going to move on from this example and talk about the next one, the bouncing ball. Every classic hand-drawn and computer-animated, whatever what have you, uses the bouncing ball as a demonstration of how you might go about learning things. I've done a right quick bouncing ball here. Your ball may not have as much spring in it as it hits the ground, but, you know, it all depends. This could be a tennis ball filled with super balls. But what the bouncing ball does is it tries to show momentum lost through, well, I guess it shows a lot of things, but it's showing how you lose energy the more you impart. Like, as the ball goes down, the first time it reaches this height because it's got so much energy, and then the next time it only gets to here, and so on and so forth. And if I did it right and it was bouncing in a vacuum, then these would be some kind of equal whatever, like slope or some kind of graph. But you know, if you get pretty close, it'll look fine. Anyway, the idea being that each time the ball hits the ground, it loses some of its power, energy, to squashing, and it pushes the ground downward as it pushes itself back upward. So whatever it gave to the ground, it loses right here. Bouncing ball, try it out. You don't even have to go left to right. You can make it bounce in from this side. There's like everything. You search bouncing ball animation tutorial and you'll see 1,000. Really what you're going for is something that looks smooth and looks realistic. The bouncing ball. There you have it. And then at the end, I like to make it roll a little bit, as if to say it's run out of bounce, and all it has now is no more up and down, but only to the right energy. And there, you see it there. Bouncing ball. Hey. It's about bouncing. Moving on. I don't want to talk about the bouncing ball anymore. Let's say you had an object that was falling, and it wasn't just going to hit the ground, but instead it was going to hit something, and then it would not be falling straight anymore. It would be flipping all over the place. Well, here's what that might look like. Hit it right there. See that? So, okay. Right now it's falling straight, and it's falling flat because it was let go flat. And then the moment that it hits something, that's no longer true. Imagine you were in outer space, and you were in a spaceship, and you had a pencil in your hand, and then, assuming there was, I don't know, let's say it was in like actual outer space where there was no air inside of a spaceship, and then you just started spinning it, it would spin and spin and keep going at the exact same speed until it interacted with something and gave away some of its energy. Here, what you're trying to replicate that perfect spin as it falls through the air. Like, imagine you were skydiving and you had that pencil with you and you spun it in front of your face, right? Relative to you, it looks like it's just sat there spinning, and eventually, because of air resistance, it would probably teeter off and then just fall like a pencil would. But if you know, if you were in a vacuum, that wouldn't happen, And usually stuff doesn't fall long enough for that to become a thing in animation where air resistance takes over. But like, you can look at it yourself in your house, like hold a pencil and then jump and toss it up as you jump at the same speed that you're jumping, but also give it some spin. And then you'll watch it in front of your face do like that floating spin thing where it's in free fall and you're in free fall, so it looks like it's just there. That's what you're trying to get at when stuff falls and hits other things, and it's just spinning in general. It's like, it's consistent. So from this frame forward to right about there, it's like, it's the same amount of rotation every time. So like that right there, let me turn this on. This is the same. Here, I'll do little angle markers. That's the same. That's the same. If you could see this right next to it, it would look like this. That's the same. They're all the same amount of degrees. That's what you're shooting for. And then if it hits something else on the way down, like right there, it'll push this whole thing that way, like it does. Put some space. And then it gets it away from the wall. And then whenever anything hits the ground, depending on what it's made out of, like, you know, if you throw a 2x4 on the ground, it won't bounce as much as if you throw a baseball on the ground. So like, this is oblong and it hits the ground pretty flat. So like, there's a lot of oh boy. Two things are happening to this object right now. It's falling down, and then ever since it hit right here, it started moving out this way. Because it didn't hit dead center, it turned this whole thing into a big lever, and then it treated where it was hitting as the fulcrum. You know, like you've got a lever, or a seesaw. This is the fulcrum, and this is the lever. Anyway, the point being, it hits right there, and it starts to rotate around that point. Then as it falls, it kind of, it starts to rotate back around its center. This was just a push in one direction. And what the push did is make it start going that way. And so it does, and then even here, again, it gets even more motion to the left. And so when it hits the ground, it's going this combined direction. So it'll bounce back up in an, like, if this was a mirror and this was a light ray, it would bounce kind of like that. So if you were standing here, you could see reflections that were over here. It'll be an equal angle going outward, just like it does. And also there'll be friction here. So many words. Once this makes contact with the ground, it'll have friction, like if you were dragging a pencil pointy end down towards the ground. And that'll start stopping it. And then after a certain point, this momentum from the bounce will die off, and gravity will take back over, and then it will start falling to the ground. Yeah. And it'll look maybe something like that. Possibly. Moving on. Let's say you got little objects and you got big objects. Okay? Little objects almost always don't weigh as much as the big stuff. Maybe this is made out of lead and this is made out of foam, but let's just say that they are both made out of lead for this case. You got a little object flying at a big object. Here it comes. Click, it hits it, and this tiny thing bounces right off, like some kind of basketball hitting a concrete building. Okay, there it goes. But this big guy, this washing machine, getting hit by a bowling ball, doesn't move nearly as much as this one seems to be. And this was the one that did the hitting. Because it's heavier. It has more mass. You know, just think about it. You ram into the side of a car, the car's gonna wobble, but it's not gonna move as much as if the car hit you. And again, here's that friction happening. Right there. That's why the whole thing doesn't slide. It's because it's still got all of this mass, and all of that weight has to go somewhere. So it puts it into the corner here. For whatever reason, you know, because it does another lever situation, right? Now this is the lever, and this is the fulcrum. And so when you hit it here, it pushes down from where it hit, and it starts putting force here, which will rotate it that way. And you can see that in action. Let me lock these off. Right here. Just like that. And there it is. Some kind of magic. And then this one bounces off. And it'll follow a path as it goes. And there's that rotating happening again. Here's 1 degree marker, here's another, and another, and just try and stay consistent, where each time it rotates, it rotates by a similar amount. And there's leeway, but you know, if it's close, it'll look fine and right. And then try and keep the center, like this object, this one right here, it has a center of mass. I'll make it easier to see. It's right there. In fact, I'll make it super easy to see. If I think I can do, yeah, that'll be good. So there's its center. You're trying to keep the center of this thing on some sort of consistent path that makes like a line that's equal on both sides. And of course there's style choices that would, like, some people like to make stuff go up really high and then down really steep like that. And like sometimes some people do like it shoots out and then it starts going straight down. It's just cartoony, given a look to it, but in general you want some sort of consistency trend. I messed up on this one, and that's on me. It was supposed to be more like here, but I didn't. Well, maybe that was just my dots, but yeah, it's off, and it shouldn't be for making stuff look right and real. In fact, this whole curve is wrong. Well, I mean, I like the way that it looks, but realistically it should be something more like that. If you want to follow suit with whatever is true to real life. But, I mean, it looks close enough. It doesn't look bad. Like, it's not hard to look at. But anyway, remember that all that stuff, the pushing here, the friction here, the fulcrum, good grabbery. Let's see the opposite. Maybe this little guy's the one getting affected. Ooh, we're gonna have to talk about squashing. So, when you animate stuff, there's something called squash and stretch. You could see it here in the bouncing ball. When it starts to fall, to give the illusion that in this frame there is a ball that is moving from the front being here to the front being here, the ball would only take up this much space. So you might stretch it to give it that look as it goes through, that it's elongating each time it moves faster. It's kind of like adding a trail or adding a blur, but it's different. It's called squash and stretch. And I'm going to do a video about it in figure animating for like stretching the boundaries of, like when you're throwing a punch, your arm might go farther than it actually is lengthwise, just to add like power to that punch. Or I don't know, stuff like you got something on the end of a rope, the rope might stretch even if it's like a chain, just to show how much tension is in the rope. But let's watch this. When this big huge thing comes down, something is gonna have to happen. And what's not gonna happen is this is gonna get pushed through the floor, because it can't. The floor is it's unbreakable. So either it's gonna get out of the way like I animated, or maybe it would have squashed. Let me turn on the onion skin. Maybe it would have just taken the brunt and squashed right down and not moved off to the side like that, and then shot out like you do when you get crushed on a corner by something. Or maybe even if you wanted to, you could have it start like a tall object, and then instead of squashing it all over, you could break it up and then just squash it right here. You know, kind of break the rules a little bit on what this is made out of. Like it could be metal. This thing could be diamonds, but you can still, for animation's sake, give it a little squashage and it'll look fine. Right there. It's like when you got those little desk clips that are black and silver, and you push down on one end and then let it shoot out. You're squashing it, giving it some sort of elasticity, and then letting it release that squashage in some which way. There you go. Next, let's talk about things that swing. This goes hand in hand with that whole rotation stuff. So if you have a normal thing that swings, it might look like this, where it starts up here, and you just do that whole easing thing where, you know, it moves a little bit slow in the beginning, and then it speeds up as it goes down, and then in this arc it gets to the peak, slows down, and then speeds back up again. I should have prepped this. But now you get to see some physics animating in action. A lot easier with onion skin on. And then as it reaches the end of its cycle, it'll come to a close. Swing, 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 swing. And slipping in some frames at all the slow points always helps, so that way you don't have to go in and manually animate those frames. Just like that. And it's a little bit dramatized for animation's sake, and that's just kind of the way that I do stuff like that. But in real life it might fall a little bit more consistently with not such huge gaps between, but it's all up to the way you think it should look. But these are just some concepts to keep in mind. Anyway, say you've got a double pendulum going on, a little two-weight action. Well, let me talk you through what it might look like. So this one is going to be pulled from here, and this one is pulled from here. I get a different color. So first of all, these are both going to be moving in tandem, but there will reach a point where the frequencies get off. And let me watch. Right there. Okay. So after this one swings down, it starts to pull on this one. Kind of like here. Watch. It reaches here, and it's still being pulled by this. And it's still being pulled by this here. But after a certain point, right here, now this is getting pushed, kinda, by this thing, because it's attached to it. So like, it'll move backwards, when if this wasn't on here, this would have just kept moving forward up to a little bit lower than the opposite of where it started. But now it's got a second weight on it. Alright, so this weight, while still swinging, is now imparting a different kind of energy to this guy here, keeping it from doing what it normally would have done. And then double pendulums tend to follow a shape kind of like this, where it loops back up. Here, just watch. Just like that. So things can be pulling on other things from totally abnormal directions. Like now here, this thing, it starts to push this out because it's getting swung up this way. You know? How do you even begin to describe something like this? This was maybe a poor example for this level of starting off-ism. But hey, I sure did it. That might be totally true to real life, but I think it's sort of close. I'm gonna visit this again later, because there's a lot going on there. But this is something simple. Say, you know, you've got your big stuff, like this. That's, you know, that's like a quarter, maybe a sixth of the size of this thing, and it'll do some damage. But it's only moving maybe 3 of itself per frame. Like 1, 2, 2.5 of itself per frame. What about bullets, huh? Bullets move fast. Like stupid fast. So they probably have a lot of force in them. Well, you would be right. And there's a formula for calculating newtons, I guess, is what you would use to measure force. But it's basically just simplify it for animation. It's weight over velocity? I mean, just think about it in your head. Big or little stuff that moves fast has a lot of force. Big stuff that moves equally fast has more force. But big stuff that moves slow, you know, it would probably have a similar force as this fast stuff moving, or the fast stuff that's little. Right? Like, you throw a dishwasher at the speed of sound, and it's gonna do some damage. But you shoot a bullet at the speed of sound, it's gonna do less damage. But say you throw that same dishwasher maybe 20, 30 miles an hour, it might do the same amount of damage, you know, overall, as a bullet would. And then, you know, bullets that move as fast as you can throw them, I mean, you can imagine that's not going to do much. So this is a big, heavy thing. Let's watch what might happen if you shot it. Can't even see the frame, but oh, it cuts it right in half. Oh dear me. Which makes me want to talk about something. So with Flash, you are a 2D animator, beyond a doubt shadow, and you have a choice to make when you are a 2D animator, and that is to stick with 2D stuff like that and just animate it as if the whole world existed only in 2D, like an ant farm that you were only ever looking at from the side. Or you can try and give the illusion of as if there was like a plane of happening here, and maybe this thing was actually like it had thickness. You know, and maybe you might start to draw this little top bit here as if it was that, but that takes longer. And it's a lot easier to... These are 2D physics, and they don't work precisely the same as 3D stuff might. But these are what I'm going to talk about, you know, for the sake of Flash animators. I might do a tutorial later on fake 3D interactions in a 2D animating scene, but that's a maybe. Anyway, a bullet is going to come in here, and it's going to impart so much force, in fact, that it doesn't even leave all of its force behind. It takes some of it with it, and it spends some of it by splitting this thing in half. Just like that. But say that this was made out of, you know, steel, or something bulletproof, instead of whatever this is. Maybe this is like charcoal or graphite. Then it might knock this whole thing over, you know, do some of this action, if the bullet were to get, like, stuck in the middle, and give away all of its energy. But that is not what happened. It was so fast that it just cut it right in half. Yeah. There's a bullet example. Now let's talk more about that whole squash and stretch action. It doesn't even necessarily have to, like, actually ever have a frame of something being squashed, but like here you can just give the idea of, say these were not these aren't made out of rock or metal or anything that is brittle. Maybe these are made out of foam, or not jello necessarily, but rubber, you know, stuff that if you threw it at the ground, it would, you know, it wouldn't just hit it. Here's what these falling on top of one another might do. Spring right there. Look at that. You see that? They come down into each other. Once the first one hits the ground, the second one would keep going, and it hits the first one, and then the third one would hit that one, and it all piles up. And eventually they all have nowhere to go. So they have to go somewhere. And since they can't go through the ground, and everything has imperfections, they're gonna pick the path of least resistance, and they're gonna go out that way as fast as they can. And imagine this like a spring, like that. Once it compressed down, it would either perfectly get little, like this, or more commonly, as things tend to happen, it'll choose an imperfection and just jut out in whatever way takes the least resistance, like these. Right there. That would be if these were like foam or something like that. If these were metal, they would just stack right on top of each other. Metal doesn't bounce. So they would just like hit and clank and maybe slide side to side just a little bit, but they would slide. They wouldn't turn the whole thing into a spring like this. Yeah. Stuff. Boing. And each time that I keep animating all these reactions, I might do a video where I just do a bunch of those hand by hand, but it's those same concepts. Like, you know, these are just spinning in the air by a certain amount each time. and the center of it is going along a path. Well, not that path, one more like that. And then as it hits the ground, you kind of have to pick where it hits, which I'll talk about in a second. And then you just see how fast it's moving and how much friction it would have and slow it down over time. And then there's that original distance decreasing with each frame easing concept. You can see it in action. I'll highlight the corners. There's one, there, yeah, and then it just gets less and less with each progression. And then you just do that for each one by itself, going through frame by frame and looking at what would happen to it. Yeah. Next, maybe you got something that's spring-loaded. Maybe you got a box that's got a lid, and that lid has a little spring inside. You're gonna be doing just more of this classic stuff. This easing, and the distance will change as it goes. So maybe something's coming out of this box really fast, like I don't know, some kind of missile. There it is. It's got its flaps. And then it's gone. So here is one lid marker. There. It just slows until it comes to a stop. And then it starts to go back. And as it goes back, it does just the same stuff in reverse. And it's up to you how fast those distances change. And it's just something that you start to do instinctively over time. You know, easing in and easing out. This one is easing out, where as time goes on, the distances get closer together. And then this one is easing in, starts slow, and then over time, the distances get bigger as it goes faster. And it might look like this. And then it's just the same stuff, using rotation to, you know, ease in, ease out, ease in, ease out for bouncing. Okay, now, before I talk about the shutter concept, I want to talk about things you can do to practice all of this jazz. Stuff that helped me learn how to get a better handle on animating stuff interacting with the world. First of all, do like 1,000 bouncing balls. Do as many as you can. The one that I have here is not that great, and you can get it a lot better and a lot nicer than this. Just throw a bouncy ball in your driveway and see what happens. Watch it like over and over, like 200 times, until you know how to do this, like in your heart box, from memory. You know, there's just maybe just do like 3 bounces. Do 1 bounce. Just animating reactions where it comes in and leaves at the same angle, and then with each frame it has less height to where eventually you just know this stuff. And then also just random particles. Here, I just did this real fast. I'm going to do another one, just as a demo. Get in a new document, get your brush tool, and do this. Get 1 finger on F7 and 1 finger on your mouse or your tablet, and just do some of this action. Have it slow down at certain spots, maybe go in a circle, and speed up, and then slow down, and do like longer strokes for when it's stretching, because it's moving more quickly, and you have to represent more instances of this one particle with just a single frame, and then have it leave, and it's gone, and do some double frames in there to make it nicer. Each time it starts to slow down, just hit F5 on those frames a few times, you know, and get to the point where maybe you do like 5 of these, all in the same document, all moving together. It's going to help you get the groove of just instinctively measuring out like distances in half their previous size increments, like that. Like these 2 dots should be about half the distance from here to here, and then these 2 should be half that distance if you want to get a good gradual ease. And then, you know, you'll start to pick up on this stuff. Practice with some of those things. Next, to get that whole free fall, rotation, what stuff looks like when it's falling and it's not falling straight, do some of this. Just that. Just get a line and have it come up into frame and leave. Right there. That's all you gotta do. And do like 20, you know? And after a certain point, you'll get the groove of making it rotate the same amount each time, regardless of how much it's moving up or down. Because you have to always couple that. And then start pairing that in with maybe making the whole thing move in a big arc, like it was thrown, but it's also spinning, like a baton, you know? And that'll be good for you. Like, some of this. Oh, I'm gonna do it on the fly here and it's not gonna look great. Yeah, I don't even want to, this might look bad, because it's not, it's harder to do it after the fact than while you're animating it. You know what, I'm not even going to show you. You see what I'm saying? Make it go in a big arc. Okay, now that I've talked about all of that, I want to discuss a certain topic of interest that happens when you animate. So all you can do, ever, is animate at a certain amount of frames per second. And this problem can be avoided if you go up to higher FPSs, like 48 and 60, but at 30 and 24 and 18, whatever, you may at a certain point run into this problem where you don't have enough frames to show a certain motion. And think of it like this. When you're on the freeway and you look out the window and you see other cars next to you, you can only see so fast, and you start to lose motion. What this is just a line that I have rotating, I think it's 10 times, counterclockwise or clockwise, and it starts slow, goes fast, then ends slow. Here's what it looks like. Doesn't look that bad if you just play it through, but if you analyze it frame by frame, there are times when you simply can't show 10 rotations with this many frames at this easing level, you know, starting slow. Because in the middle here, you're trying to convey a rotation where this line right here ends up going all the way to here. You know, and like, how do you show that with just a single frame? Well, either you don't, and you just skip it, or you use a trail, like a lot of people do with swords, and sometimes really fast punches, or you pick the best fit frame, because your timeline it's like a camera, like the inside of a camera, and the way that they work is they have shutters that open and close to let the light in for a split second, and there's a little door just like this in front of your sensor, and it'll go up and then it'll go down. Some go side to side. The point being, it can only be open for your frame rate. So it can only ever be open for 1/30th of a second. And sometimes you might miss a whole rotation right there. And you start to get this weird, like, oh, it's open now, and then it moves, and wait, what happened to it being right there? You can't see it. And you might start to run into stuff like where you're animating and you go along and you have this perfect motion all planned out, but you get to where, like, you know how big the space should be between this line and this one, and it's all looking good, but then there's this gap right here, and the next space would be vastly bigger than just having it go down this far, where it would only be that big. But if you don't see the box make contact with the floor, then it looks out of place. Even though, like, frame-wise speaking, everything you did is correct, not having a contact point is weird. So you can either, like, smudge the boundaries and do some of that, and it'll be fine, or you can just disregard what you thought was right for the motion and make it go maybe farther than it actually would have in just one frame, like this, and you can generally pull it off. Or you can add a trail, but that doesn't really work in this example. But just keep that in mind for when you're animating. Sometimes you have to do certain motions that might not make sense exactly, like this. It seems just a little bit too far, like it's falling too fast too quickly. And you could maybe, like, put a second frame before it, or kind of change the frames leading up to it to where you put an extra one in here and then you slip one right here, and that might make it look a little bit better. But yeah, and the effect becomes a lot more obvious at lower stuff like 18 and 21 FPS. Generally 30, 36, 48 is safe most of the time. But yeah, time for some closing thoughts on this intro to physics in animation. You know, sometimes a bowling ball can have the same force as a bullet. Just depends on how fast it's going. So, you know, don't ever skip out on animating someone flying back from a bullet hit just because it's a bullet. Unless it goes through them, then obviously they wouldn't fly back as far because some of the energy is still left in that bullet. But if it doesn't, if it just hits a bulletproof vest, then hey, you know, make them fly back. All that energy went somewhere. These easing motions, and if you want to get a quick, well, I'll wait for the tweens tutorial. Just practice your particle thing. You know, making this look good and fluid and like it has purpose. Like each little swoop is, you know, smooth looking. And then lastly, this whole idea where sometimes you might miss a frame. Like on here, it should be contacting the ground, but it's just not. You know, just smear the frame. Just ignore it and put this here. And then where it would have been, you can just say that it was actually there, and it's fine. Yep. Look at life, you know. See what happens with stuff that you do in your house. Drop some books, launch some missiles, do some damage. Thanks so much. I'm Andrew Bepler, and you know, I guess I'll see you.